Wings in an aircraft generate lift, and lift is the upward force which enables the aircraft to take off, climb, and as a general stay in the air. There are different shapes and designs of the wings which differ from one aircraft model to another, but as a general, all wings follow the same rule and principle of generating lift, which is directly related to the Bernoulli's principle. What is Bernoulli's principle? Bernoulli principle related to the fluids, gas or liquid, states that when a fluid is flowing inside of a tube or is flowing over the surface, the amount of the pressure that the particles of the fluid impose on the surface or impose on the surrounding walls of a tube is indirectly proportional to the speed of the particles of the fluid. This means if the speed of the particles of the fluid is high, the amount of the pressure that they impose on the surface or on the surrounding walls of the tube decreases, and as much the speed of the particles of the fluid decreases or they flow with a lower speed, the amount of the pressure that they impose on the surface or on the surrounding walls of a tube increases. Same principle goes to the wings of an aircraft. So in order to help the wing to generate a lift, we need the particles of the air flowing on the upper surface of the wing to flow with a higher speed, and the particles of the air which flow on the lower surface of the wing to flow with a lower speed. But based on the Bernoulli's principle, the particles of the air should reach at the trailing edge of the wing at the same time. This does not mean that the particles of the air flowing over the upper surface of the wing should reach the trailing edge of the flap before the particles of the air which flow under the lower surface of the wing. If this condition happens, then there will not be any lift generated. So based on Bernoulli's principle, the time with which the air particles touch the leading edge of the wing and they divide into two parts, one part flowing on the upper surface of the wing and one part flowing on the lower surface of the wing. Higher speed over surface, lower speed lower surface should reach at the same time at the trailing edge of the wing. So generally around a wing we have two pressure areas. We have a high pressure area on the lower surface of the wing, and then we have a low pressure area on the upper surface of the wing or upper side of the wing. The difference of these two pressure areas, the high pressure area and the lower surface of the wing and the low pressure area and the upper side of the wing, the difference of these two pressures will generate a resultant force, which is an upward force and which is called lift, which acts from the CP or center of pressure of the wing upwards. This is the force that enables us to take off, this is the force that enables us to climb, and this is the force that enables us to stay in the air. During the flight in different regimes, starting from takeoff to initial climb and then climb, cruise, descent, approach and landing, we need different amount of the lift to be generated from the wings. In two regimes of the flight, mainly the takeoff and the landing, we need the wings to generate as more lift. So why we need the wings to generate more lift? Because we have lesser speed. So three factors which affect the generation of the lift from a wing are the curvature of the wing, and then the area of the wing and speed of the air which blows around the wing. Since during takeoff and landing we have lesser speed and lesser speed of the air particles which flow around the wing, so in these two regimes of the flight we need the wing to produce more lift having lesser speed. How we can do this? It is possible to increase the surface and the curvature of the wing by movable surfaces that are installed in the leading edge and in the trailing edge of the wing. During approach for landing, the same. We have lesser speed, so lesser speed means lesser lift generated by the wing. but increasing the surface, increasing the curvature of the wing will enable it to generate more lift, and more lift will enable the pilot to reduce the speed, because we're coming to land on the runway with lesser speed. The landing speed is lesser than the descent speed, lesser than the, for example, cruise speed. To increase the curvature of the wing, okay, it helped the wing to generate more lift, but besides generating more lift, increasing the curvature will produce another problem, and this problem is that the hair which flows over the upper surface of the wing due to more curvature will not be able to flow smoothly and fluently on the upper surface of the wing, and some eddies, some currents will be generated. These eddies or currents on some over surface of the wing will increase the drag, and we should control this. Later we will see how we are controlling this. Generally, in the leading edge of the wing, the movable surfaces attached are the leading edge flaps and leading edge slats. Mainly we have two leading edge flaps in the leading edge of the wing, inboard of the engine towards the fuselage where the wing is thick, and then we have three panels of the leading edge slats outboard of the engine towards the tip of the wing where the wing is thin. So since the wing is thick in the area where the leading edge flaps are connected, when we extend the leading edge flaps, so curvature of the wing will not be affected. This is a factor that we should consider always. But in the area where the leading edge of the wing, the design is thin outboard of the engine towards the tip of the wing, when we extend the leading edge slats, curvature will be increased, and increased curvature will produce some eddies, some currents on the upper surface of the wing, as we said before, which will increase the drag. How we should prevent this? The manufacturer has found a very good way and an excellent way to prevent this. So when we extend the leading edge slats, slot will be produced, or in general words we can say that slots will be made between the leading edge slot and the leading edge of the wing. These openings are there to help some portion of the hair from the high pressure area, which is in the lower surface of the wing, to blow towards these openings on the upper surface of the wing, and this portion of the hair will push the eddies or currents which have been generated on the upper surface of the wing backwards, and then we will have a smooth flow of the hair on the upper surface of the wing. So problem of the curvature will be solved, mainly in the leading edge of the wing, but still we have the problem in the trailing edge of the wing. When we extend the trailing edge flaps, we will look at it later. The leading edge flaps has only two positions, which is the extend and retract. And besides, we do not have any anti-ice system available for the leading edge flaps, because they are attached in the area where the wing is thick. Then in the leading edge slats, we have three positions. The first position is the retract position, and then we have the extend position, then we have the full extend position. And because the leading edge slats are in the portion of the leading edge of the wing where the shape of the wing is thin, so besides that curvature problem that we talked before, there is possibility of ice buildup on the leading edge slats. So we have anti-ice system to prevent this. So during the flight in the icing conditions, the leading edge flaps and slats is totally controlled. The movement, I mean, is controlled by the trailing edge flaps mechanism. We do not have any separate mechanism to extend or retract the leading edge flaps and leading edge slats. It's totally controlled by the movement of the trailing edge flaps. So as much as we extend the trailing edge flaps to any degrees, same movement will be transferred to the leading edge flaps and slats, and they will be also extended. Extending the trailing edge flaps up to 5 degrees, will extend the leading edge flaps to full extent because they have only one position, but will extend the leading edge slats to the extended position, not the full extent. So we have one position more for the leading edge slats, which is the full extent. If we move the trailing edge flaps behind 5 degrees, then the leading edge slats will be moved to the full extent position. There is another automatic system which will move the leading edge slats to the full extent position. This is done by the auto slat system. The auto slat system is powered by the hydraulic system B. So for the auto slat system to function, we need a hydraulic system B available. We should have it. If we do not have hydraulic system B available, the auto slat system will be inoperative. When the auto slat system will extend the leading edge slats from extend to full extent, that is during the takeoff. For example, if we take off with lightweight, with the half center of gravity, and with the engines producing maximum thrust, so during the pitch up, when we pull on the column, so if excessively we pitch up and the amount of the angle of attack is more than the limit, then the aircraft will go to a condition of the stall. To prevent the stall, the slat system will move the slats from extend to full extend position. This is totally automatic, not under control of the pilots. Then when we decrease the pitch up angle or decrease the angle of attack, so in this case the auto slat system will move back the leading edge slats from full extent back to the extend position. The full extent position of the leading edge slats will help us to increase the angle of attack to a predetermined value, but still if we pitch up behind that limit, so the aircraft will go to the stall. I'm not sure that you accept my wording or not, that if I say that if we increase the angle of attack behind the limit and even the leading edge slats are moved to the full extent position, the aircraft will go to the stall. This is not true. Why? Because before the aircraft goes to the actual stall, there is a warning which will be brought to the pilots by shaking the control columns, and the control columns will shake. In this condition, we are not in the stall condition. Still, we have some degrees of the angle of attack that we can increase. So this is only a warning for the pilots that, okay, the aircraft will go to stall, please do something, and the only thing we can do is to decrease the angle of attack. But still, if we continue increasing the angle of attack, then the aircraft will go to the actual stall. Anyhow, as we said before, the normal system which drive the leading edge flaps and slats is the hydraulic system B. So what happens if the hydraulic system B, for example, gets failed, or we have the failure of hydraulic system B? Then we can extend or retract the trailing edge flaps by another alternate system, and we can extend the leading edge flaps and slats by another alternate system. Now the difference comes here. So we have different alternate systems to drive the leading edge flaps and slats in case the normal hydraulic system B fails. So they have giant, for example, movement when hydraulic system B is available, but once the hydraulic system B gets failed, then the system separates. We have alternate system for the leading edge flap and slats. We have another alternate system to drive the trailing edge flaps. The alternate system to move the leading edge flaps and slats is the standby hydraulic system. Based on the non-normal checklist, once we need to extend the leading edge and trailing edge flaps and slats, we should move the alternate flaps master switch from guard and down position to the up position, and then it will help the system to pressurize the standby hydraulic pump. The standby hydraulic pump will be pressurized, and then standby hydraulic will be available for the leading edge flaps and leading edge slats. We have the actuator for each flap and slat panels. So these actuators will be pressurized both from the normal hydraulic system B, in case system B not available, from the standby hydraulic system. We have, for example, selector valves. We have three-way selector valves when the hydraulic system B is available. Then we have only two-way selector valve when hydraulic system B is not available. Having a standby hydraulic system has an alternate method. We can only extend the leading edge flaps and slats. We cannot retract them back. This is a phenomena that is talking is easy, but once the leading edge flaps and slats are extended, in case we make a go around, we cannot make a successful landing, we cannot retract the leading edge flaps and slats, in the climb performance and later the cruise performance, if we proceed to an alternate airport, will be degraded because we have the panels extended. Coming back to the trailing gauge flaps, the common type of the trailing gauge flaps incorporated or used in Boeing 737 Classics, NG and MAX is the slotted Fuller flaps. As a general, we have two types of the Fuller flaps, which are the double slotted Fuller flaps, and we have the triple slotted Fuller flaps. In Classics, we use the triple slotted Fuller flaps. The Fuller flaps are very excellent trailing edge flaps, because when we extend such type of the flaps, besides making the wings curve or increasing the curvature of the wing, we increase the area of the wing as well. Why? Because the Fuller flaps, once extended, they get two movements. The first movement is the downward movement, and the second movement is the backward movement. So on the tracks when over which the trailing edge flaps move, once we extend them, so they get two types of the movement. They come down and they go aft. So by this way we increase the area of the wing, and at the same time we increase the curvature of the wing, and more lift will be generated from the wing. The triple slotted Fuller flaps, once extended to the full degree, which is the full extend position, which is the 40 degree. If we look at the trailing edge flaps, there are three panels. We can see the three panels, and they are the fore flap, mid flap and aft flap. Between the fore flap and mid flap, and between the mid flap and aft flap, and then back between the fore flap and leading trailing edge of the wing, we have three openings, three ways. Because of this, it is called the triple slotted Fuller flaps. These slots or these openings are to prevent the creation of the eddies, creation of the some for example currents on the over surface of the flap, because curvature increases. Same principle that we explained before for the leading edge flaps and slats. So some portion of the here from the high pressure area, which is in the lower surface of the wing, will flow towards through these openings on the upper surface of the flap and push those eddies backwards, and will just ensure the smooth flow of the here on the entire upper surface of the wing, starting from the leading edge up to the end of the Fuller flap, if you extend them up to 40 degrees maximum, for example. The trailing edge flaps are normally extended and retracted or operated by the hydraulic system B. So we should have hydraulic system B available to extend and retract the trailing edge flaps. If hydraulic system B is not available, then we have electrical system to extend or to retract the trailing edge flaps based on the non-normal checklist. So we should move the alternate flat master switch, which is on the aft overhead panel of the overhead of the captain, from the down guarded position to the up position, and then once we move the alternate flap position switch to the down position, electric motor will be energized and the trailing edge flaps will be extended to any degree that we want. The controls in the cockpit for these high lift devices is a lever, which is in the control pedestal in the right side, so we can select 8 degrees of the trailing edge flaps extension, starting from 1 degree to 2, and then 5, 10, 15, then 25, 30, and 40. Normally in class 6 we are taking off with flaps 5, and normal flaps for the landing. The trailing edge flap for the landing is either flap 30 or flap 40. In some of the airports where the climb performance is a factor, in case of the go around, we are normally landing with flaps 50. It is possible. So in the detains that we move the trailing edge flap lever, and detain number 1 and detain number 15 we have gates. These gates are for fast selection of the go around flaps in case we are landing with both engines. So if we perform the go around, the gate and 15-degree detain is to help the pilot to select the go around flap with 2 engines, which is the flap 15, and the gate in the 1-degree detain is for the pilots to select the go around flap in case we are landing with single engine, because in single engine we are mostly landing with flap 15, so the pilot can fast select the go around flap when we are performing the landing with only 1 engine. Regarding the drive mechanism of the trailing edge flaps, the mechanism is in the main wheel well in the forward wall. We have an electric motor, and then we have an hydraulic motor. The hydraulic motor is normally pressurized by the hydraulic system B. So once hydraulic system B is for example directed to the hydraulic motor, the motor will start turning. So we have 2 jack screws in the right side and the left side, which is connected to the just the tracks which is moving the trailing edge flaps. Still we have jack screws, and then the jack screws will move and help the trailing edge flaps to drive on the track and to get 2 movements, downward and backward. If hydraulic system B fail, then we have an electric motor which is also connected in the same drive mechanism of the trailing edge flaps. The electric motor will be energized and same drive mechanism will be moved. So the only difference here will be that electric motor will be operative, hydraulic motor will be inoperative. Having said before, the normal flaps for the landing is either flaps 30 or flaps 40. So in order to prevent excessive load and stress and damage on the trailing edge flaps, mostly when we come for the landing, because sometimes it happens that the speed during the landing increases, we have a load relief system on the trailing edge flaps. The load relief system of the trailing edge flaps comes into effect or arms when the trailing edge flaps are extended to 40 degree. So if the speed during the approach for landing increases behind a predetermined limit, the load relief system will automatically move the trailing edge flaps from 40 degree to 30 degree. This is because to prevent the flaps from being stressed and damaged due to the high speed. But the lever still remains in the 40 degree in the cockpit. This is also not under control of the pilot. This is fully automatic, and the pilots can see the trailing edge flaps indicator that the pointer moves from 40 degree to the 30 degree. But once the speed decreases back to the normal limit, the flaps will automatically move back from 30 degree to the 40 degree. This is a very good system which prevents the flaps from being stressed or from being damaged. One common mistake among the pilots when they perform short approaches, mainly in V4 airports, is to decrease the aircraft speed by extending the flaps. But we should keep in mind that the flaps are not there to help us to decrease the speed. Okay, if we have the proper position of the flap with the proper speed, okay, we can reduce the speed for the next flap extension, but it's not the proper way that we should use the flaps as the speed brake. But it's commonly just mistake among the pilots. For example, they have higher speed. In order to reduce the speed, they extend the flaps. This way we damage the drive mechanism of the flaps, and this way we bring more stress on the flap drive mechanism, which will be very costly for the company to pay for the repairs. And flaps are only there to help us to have more lift on the wings. They are not speed brakes. They are not the panels that help the pilot to reduce the speed. So this common mistake should always be avoided, and we should always keep in mind that what the usage of the flaps are during the flight. Since flaps are the movable surfaces, so same as other aircraft systems, it's possible that we get some problems during the flight extending or retracting the flaps. And two common types of the problems associated with the trailing edge flaps are the split and asymmetry flap extension, or the problems. Please keep in mind that we have systems of protection in the flap. So asymmetry means that the trailing edge flaps in one wing extend to 1 degree or any degree, and the trailing edge flaps in another wing extend or remain in different degrees. So this brings gives the asymmetry for the aircraft. In order to prevent asymmetry of the aircraft, in order to prevent damage from the trailing edge flap drive mechanism, we have a bypass valve. When the bypass valve feels that there is an asymmetry extension of the flaps or asymmetry retraction of the flaps, the drive mechanism or the drive valve will move to the bypass position and bypass the hydraulic pressure from the flaps, and the flaps will be stuck there. And then we have another problem associated with the trailing edge flaps, which is the split flap. Split flap here means that for example, lever is moved from any degree to the higher degrees, but the flaps are totally not moving in both sides, from left and right. There is not asymmetry, but they are totally stuck and they are not moving down. Mainly this problem comes into effect if there is a damage or there is some problem in the drive mechanism. So based on the non-normal checklist, we try to extend the flaps by alternate method, by electric motor. This is one way to get rid of this problem. But if we have asymmetry, for example, in one wing we have 1 degree of the flaps, in another wing we have another degree of the flaps, we are not allowed to use the alternate flap extension method by extending the flaps by the electric system, because if we do this, we will further damage the flaps. So colleagues, thanks much for watching the video, and we had a rough overview of the high lift devices, mainly the leading edge flaps and slats and trailing edge flaps. We had a short review of the basics, how we can help the wings to generate more lift for us, and how the leading edge and trailing edge flaps and slats are extended and retracted. And if you have any questions related to the high lift devices, mainly in Boeing 737 Classics, please leave your questions in the comment box of this video. In time available, I will read and answer all those questions to you. Thank you very much. God bless all. And in next presentation, we will be still following the flight control system of the Boeing 737 Classics.